All right, next we want to talk about partial fraction expansion with quadratic factors. So here are your guidelines for solving the basic equations. Number 1, expand the basic equation. 2, look for values of x that will allow you to solve for any coefficients. 3, group terms according to powers of x. 4, equate the coefficients of like powers to obtain a system of linear equations involving a, b, c, and so on. And then finally, solve the system of linear equations, and then you'll be able to integrate. All right, so in this first example, all we want to be able to do is write the partial fraction expansion for the rational function. So notice we're not integrating here, we just want to expand this rational function. Okay, so the first thing we always want to do in expanding the basic equation is factoring the denominator. So here you can see we can take out an x, and then we'll be left with x minus 1. And sadly, x squared plus 4 is not factorable, so we're just going to leave that x squared plus 4. And we'll rewrite our numerator. Alright, so the reason for this lesson is we have a factor down here that is quadratic, and it's not factorable. And so that's why we're talking about quadratic factors. Okay, so we need to know how we can expand this into our basic equation, and we're going to deal with linear factors the same way that we did before. So these right here are just linear factors. So we're going to get a over x plus b over x minus 1. So we keep that the same. So next we need to figure out how are we going to expand with this quadratic factor right here. Well, since this is in the form x squared plus 4, we're actually going to have cx plus d as our numerator over the x squared plus 4. Okay, so that is what is new with expansion with quadratic factors. Okay, from here all the steps are the same. We just need to figure out what a, b, c, and d are, and then we will have expanded our rational function. Okay, so you'll recall the next step was to multiply everything by this common denominator. So we actually end up multiplying here, here, and here. And you'll recall when we do this, the denominator of each of these is going to cancel out with one of the factors in the denominator over here. Okay, so we can get our basic equation pretty quickly here. Okay, for our a quantity, the factor of x is going to cancel out, and so we're going to be left with the factors x minus 1 and x squared plus 4. For the b, the factor x minus 1 will cancel out, and we're going to be left with the factors of x and x squared plus 4. And then for cx plus d, we will put that in parentheses there. The factor of x squared plus 4 is going to cancel out, and we're going to be left with the factors x times x minus 1. And then we'll recall that this still equals the numerator up here. Alright, so this really is the equation that we're trying to solve. So the next step says look for values of x that will allow you to solve for any of the coefficients. Okay, so let's just look at this first factor right here, x minus 1. If we let x equal 1, then this would cancel out, and so would this. And then all we'd be left to find was our b. Okay? So let's go ahead and let x equal 1. Okay, the a factor is gone, so now we have b. And then this is going to be times 1 times 1 squared plus 4. And then the cx plus d factor is gone, so then we'll plug 1 into the right side of the equation. So 2 times 1 cubed minus 4 times 1 minus 8. Okay, and then 1 times 1 squared plus 4, that's just 5. So we have 5b equals, well, this is 2 times 1, which is 2, and then minus 4 minus 8, which is negative 10. So 5b equals negative 10. And so this gives us b equals negative 2. Alright, so let's go back up to our basic equation now and see if there's anything else we can let x equal that will get rid of any of our other coefficients. So looking at the factor x squared plus 4, notice this doesn't have any real solutions, and so this is not going to be helpful. But if we look at x, we could let x equal 0, and then we would get rid of this term. And here, if we let x equal 0, we would get rid of this term as well. And so then we would be able to solve for a right here. Let's go ahead and let x equal 0. And so we're going to have a times 0 minus 1 times 0 squared plus 4 plus, let's see, the b coefficient's gone, cx plus d is gone. So actually we just have equals 2 times 0 cubed minus 4 times 0 minus 8. So when we solve this here, we have a times negative 1 times 4, so that's negative 4a, and that's going to equal 2 times 0 minus 4 times 0 minus 8, so that's just negative 8, and so a equals 2. Okay, so as we continue to solve this basic equation, now we can substitute in for a and b, and we still need to be able to find c and d. So what we're going to do is actually multiply these factors together so that we can continue solving for our basic equation. So now we know a equals 2, and we'll multiply x minus 1 times x squared plus 4 using the FOIL method. We're going to get x cubed plus 4x minus x squared minus 4. And then b is negative 2, so plus negative 2 times, well, x distributed into x squared plus 4 is going to be x cubed plus 4x, and then plus cx plus d times, well, x distributed into x minus 1 is going to be x squared minus x. And of course, this is still equal to 2x cubed minus 4x minus 8. Okay, next let's go ahead and distribute in the coefficients here. Okay, so we get 2x cubed plus 8x minus 2x squared minus 8. And then we'll distribute the negative 2. So we get minus 2x cubed minus 8x. Then we'll distribute the cx plus d, so we'll FOIL there. So we get plus cx cubed minus cx squared plus dx squared minus dx. And of course, this is still equal to 2x cubed minus 4x minus 8. So next we're going to be looking at grouping the terms according to the powers of x. And along with that, you want to take out your greatest common factor as well. Okay, so I'm going to group all the terms that have an x cubed. So here, here, and here. And so I get 2x cubed minus 2x cubed plus cx cubed. Then I'm going to group all the terms with an x squared. So here, and here, and here. And so I get minus 2x squared minus cx squared plus dx squared. Then I'm going to group all the terms with just an x to the first. So I'm going to get plus 8x minus 8x minus dx. And then I'm just going to combine all the constants. So here we just have a negative 8. Okay, so now I want to combine like terms and take out the greatest common factor. So 2x cubed minus 2x cubed is 0. So all I'm left with here is cx cubed. In this case, I can't combine any of the factors, so I'm just going to go plus, and I'm going to take out a negative 2, a negative c, and a positive d, and that's times x squared. For the x's, I can combine 8x minus 8x, and that gives me 0, so I'm left with minus dx. And for the constants, I just have minus 8. And now notice that all of this still equals 2x cubed minus 0x squared minus 4x minus 8. Okay, so I just took this right side of the equation and I gave it the colors with the same powers of x. And so now by making the comparisons of the coefficients, I can tell that c is going to equal 2. And negative 2 minus c plus d is going to equal 0. And negative d is going to equal negative 4. And you'll notice here the constants are a wash. And that should happen just like that. Okay, so we know c equals 2. And you'll notice here we still have two variables. I could substitute 2 in for c here and then solve for d. But it's going to be much easier to solve for d here because we can see that d equals 4. Okay, so we didn't need this one right here because we have c and d. Okay, so looking this over now, we know A, B, C, and D. And so we're just going to substitute those back into our expanded fraction. Okay, so A equals 2, so we have 2 over x. B equals negative 2, so we actually have minus 2 over x minus 1. And then C was 2 and D is 4. So we get 2x plus 4 over x squared plus 4. Alright, so here is our partial fraction expansion for the rational function. Now notice there was no integral here, but if there had been an integral, then we would be able to integrate this by doing all these separately. Okay, but the biggest thing to learn here is that partial fraction expansion when you have a distinct quadratic factor. Alright, so let's try the next example. It says evaluate the integral using partial fraction expansion. So again, looking here, we would want to factor the denominator. We have an x plus 1. And if we look at x squared minus 2x plus 3, that is prime, so we can't factor it, but we do have a distinct quadratic factor. So the first thing we want to do is separate this integral using partial fraction expansion. So we're going to have the integral of a over our first factor, x plus 1, plus the integral of, well, there is a quadratic factor, so now we'll call this one, just going alphabetically, bx plus c over our quadratic x squared minus 2x plus 3. Okay, now we're going to go ahead and multiply by the denominator here, and then the respective factors, of course, are going to cancel out. So we're going to be left with a times x squared minus 2x plus 3 and then plus bx plus c times x plus 1. And this is going to equal x squared minus 4x plus 7. Remember the rest of the numerator right there. Okay, and we want to get rid of one of these terms now. So if we look at all the factors here, if I let x equal -1, this term is going to be gone, b and c are gone, and we're going to be able to find a here. So let x equal -1, and we'll substitute. So we get -1 squared minus 2 times -1 plus 3. Again, we said this term is gone, so this is going to equal -1 squared minus 4 times -1 plus 7. And when we simplify here, this becomes 1 plus 2 plus 3, so that's 6. So we have 6a equals, well, this will be 1 plus 4 plus 7 equals 12. So that gives me a equals 2. Okay, so that looks like all we're going to be able to cancel out. So now we need to look into substituting for a, okay, and then multiplying here and then grouping our like terms. So a is 2, which means we're going to get 2x squared minus 4x plus 6. And then we're going to FOIL bx plus c times x plus 1. So that's going to give me bx squared plus bx plus cx plus c. And again, this equals x squared minus 4x plus 7. So now let's group our like terms here. So this is going to give me 2x squared plus bx squared, which we could rewrite as 2 plus b times x squared. We can group our x terms together. So it looks like 3 of them there. So we have minus 4x plus bx plus cx. And we get -4 plus b plus c times x. And we'll just put a plus there. And then we have our constants. So c and 6. Those are both constants. So we'll group those together. And again, it's going to equal x squared minus 4x plus 7. Okay, so now we can compare coefficients. So 2 plus b has to equal 1, which means b equals -1. -4 plus b plus c has to equal -4. So as far as we can get on this one is b plus c has to equal 0. And for our constants, I would know 6 plus c equals 7, meaning c has to equal 1. And you can see if you substitute these in here that it works. -1 plus 1 equals 0. At any rate, now we know our a, our b, and our c, and so we can go ahead and substitute in up here. So we're going to get the integral of 2 over x plus 1 dx plus the integral, well, b is -1, so negative x plus c is 1, so plus 1, over x squared minus 2x plus 3 dx. So now let's just go ahead and deal with integrating these. So first let's deal with integrating 2 over x plus 1. That's just going to be 2 times the natural log of the absolute value of x plus 1. And next, let's deal with integrating this one, negative x plus 1 over x squared minus 2x plus 3. This is going to be a little bit tougher. What we can do is let u equal the denominator, x squared minus 2x plus 3. And that means du is going to be 2x minus 2 dx. Okay, so we're trying to get u prime here on top. Okay, so I do see an x and a constant, so what can I multiply the numerator by so that it equals 2x minus 2? Well, negative x times negative 2 gives me 2x, and 1 times negative 2 also gives me negative 2. So I'm going to multiply this by negative 2. So now I have to counteract the negative 2 on the inside of the integral by multiplying on the outside of the integral by negative 1/2. So now I have minus 1/2 times the integral of u prime over u. And you'll recall that this just equals the natural log of the absolute value of u. And we know what u is. So we'll substitute that in. And so we had minus 1/2 times the natural log of the absolute value of u, which is x squared minus 2x plus 3. And we still had the 2 ln absolute value of x plus 1. And then don't forget, because this is an indefinite integral, we have plus c right there. Alright, so there is your final answer. Alright, next we want to take a look at an example that contains a repeating quadratic factor. So when you have a quadratic factor like x squared plus 2 that is repeated, you deal with it similarly to repeating linear factors. You basically combine the two concepts together. So we can rewrite this as the integral of ax plus b over x squared plus 2. Okay, so because it was quadratic, we had to do the ax plus b, and you go over one factor, and then plus the integral of cx plus d, because we have a second quadratic factor, and now you divide it by x squared plus 2 squared. Okay, so this is very similar to what we did with the repeating linear factors. You take the first factor and then the factor to the next higher power, and you would just keep going if there were more powers. Okay, so it looks like we have our fraction expansion set up, and now we need to find our basic equation. So remember, we're going to multiply this times both of these, and we're going to lose some of these factors here. So we're going to be left with ax plus b, and then we're still going to have one of the factors, x squared plus 2, because we're only able to cancel one of them. And then for cx plus d, both factors are going to cancel, so we're just going to be left with cx plus d. And then we'll recall that this still equals the numerator, 8x cubed plus 13x. Alright, so next we're going to FOIL. So here we're going to get ax cubed plus 2ax plus bx squared plus 2b. And then we still have plus cx plus d. And it still equals 8x cubed plus 13x. So next we're going to group our like powers of x. We have the cube here. That looks like the only one. So we have ax cubed. And we'll go on to the squares. So here's an x squared. It looks like it's the only one. So plus bx squared. And then x we have here and here. So we're going to have plus 2ax plus cx. And then our constants 2b and d. So plus 2b plus d. All right, and this is going to equal 8x cubed plus 0x squared plus 13x and plus no constant. Okay, so now we'll compare these equations. So we have ax cubed is going to equal 8x cubed, and so that means a equals 8. For bx squared, there are no x squared, so that means b just equals 0. For 2a to the x plus cx, that's going to have to equal 13x. So in other words, we have 2a plus c would have to equal 13. Okay, and we'll just kind of leave that one alone for now. And finally, the constants, 2b plus d, well, there are none over here, so we know 2b plus d equals 0. So now using substitution, we can find some of these. So I know a equals 8, so 2 times 8 plus c equals 13, meaning c equals -3. And in our last one, we know b equals 0, so 2 times 0 plus d equals 0, and we're left with d equals 0. Okay, so we have our a, b, c, and d now, and let's go ahead and substitute into our expanded fraction here. So looking at our first integral, let's substitute in for a and b. So I get the integral of a, which is 8, so 8x, and then b is 0, so over x squared plus 2 with respect to x. And then here, for this integral, I get plus the integral of c, which is -3, so -3x plus d, which is 0, over x squared plus 2 squared dx. So let's go ahead and find these integrals separately, and then we can add them back together. So looking at this one right here, I might factor out my 8 to start off with. And then if I let u equal x squared plus 2, du would just be 2x. So that means I need to multiply by 2 on the inside and 1/2 on the outside. So my final integral would be 4 times the natural log of the absolute value of x squared plus 2 and plus c. And taking a look at this one, so I have something squared in the denominator, so we can do a couple things here. I'm going to factor out the -3. I'm going to take this exponent of 2 and make it negative and move that to the top. So I'm going to have x squared plus 2 to the -2 with respect to x. And with this one, I would probably let u equal x squared plus 2. And so du would equal 2x dx. And I can see I have an x already. So I would need a 2 on the inside and times by 1/2 on the outside. So now I just have u to the -2. So now I can rewrite this as -3/2 times the integral of u to the -2 du. And I can just use the power rule. So remember, I need to add 1 and then divide by that new number. So we're left with -3/2 u, well, -2 plus 1 is -1, and then divided by -1. And we'll just substitute back in for u. So the negatives are going to cancel. So we have 3/2, and then u to the -1 is going to be x squared plus 2 to the -1, which I'd probably rewrite as 3 over 2 times x squared plus 2. So now we'll just go ahead and write our final answer. It's going to be 4 ln absolute value x squared plus 2 plus 3 over 2 times x squared plus 2 and plus c. And there we go. So that is how to deal with partial fraction expansion with repeating quadratic factors.